Okay, so good morning, everybody. Welcome back. There are a few announcements first. So, there has been another change in the schedule of the lessons. Okay, I guess you get Moodle notification, but that word, in any case, there won't be our usual lecture on Thursday, December the 4th. There is the ceremony for the official start of the new academic year, and so all the lectures are suspended. There is nothing we can do about it. The only thing we should or even must do is recover those lessons. Sorry for you, but there is a minimum number of hours that I have to do with me. So the only option basically is December 16th. Okay, so it's a Tuesday. That slot was empty for whatever reason, and we will recover the last lecture there. Keep in mind that even if usually on Tuesday you start at 10, with me we start at 9, because I need 4 hours and 3 hours are not enough. So that's the first communication. Second communication, just now, yes, just now I put my exam dates. Okay, so as I anticipated, there will be no registration at the moment on the Etc platform. Okay, so the registration will be here. Tell me if you notice something weird, like incoherent dates or stuff like that. So we have the usual 3 dates, one at the end of January, one and 2 in February. They are 1 week apart. I tried to put the exam dates where in the week there were no other exams for your same year. Okay, this has not been always possible. To be honest, I think it was possible only in one of these dates. I don't remember when. Obviously, I avoided any overlap, so you won't have 2 exams the same year in the same day. But yeah, the exams will be at the San Lazzaro campus, not here. Okay, so if you're not familiar, here there is the Google Map link at the Bucola Bisi Pavilion in the San Lazzaro campus. You must book your exam from this page. Okay, so here you have 3 basically bookings items. Beware that the registration closes 3 days before. Okay, because I need to organize it. There are many of you. I need to check whether the hours that I booked the room are enough. So beware that the registration closes 3 days before. If I did no mistakes, they are already open, so you can already enroll. Usually there is no need to rush. Usually you are a few, so even if you book all the exams same day, usually we can deal with it. But assuming that for some reason you are a lot, I may need to resort to a first come first served basis. Okay, so the first who registers is the first in the list. And if we have no time, the others will be rescheduled for the day after or something like that. It never happened in the past. That's it. So please keep in mind that as I said, registration closes 3 days before. It may be useful to also submit your projects, okay, at the same time. So within the same deadline, 2-3 days before, submit your projects. I didn't yet post in the website some exemplary projects. I will this week in a section. And remember, the instructions both for the exam and for the projects, they are in the first slides that we've seen at the beginning of the course. Okay? I don't remember if they are I think they are in the administrivia slides. And also here there is there are other informations for the project, and a pool of exemplary questions for my part of the exam. Okay? As it is written here, this is not an exhaustive list of questions, but it's just to give you an example of what you can expect from the exam. I would say that for the most important communication, that's it. A minor one that I also put in the forum as usual. I also updated the last slides with an updated link to an explanation of eigenvectors and eigenvalues. It was broken, now it's fixed. So if you want to re-download the slides, now they are fixed. So today, instead, coming to our content, we will first basically end our journey through unsupervised learning with association rule mining, which is obviously a technique in the family of unsupervised learning technique, and will also give us a concrete example of what it means to do data mining. Data mining is something we mentioned in the introduction to the course. It's a very related topic. We didn't really describe what it means to do data mining. Basically, in brief, it means to try to find patterns hidden in data. So it is not something usually that you do with supervised learning. You can do data mining with clustering, obviously, and association rule mining are one of the most probably successful examples of unsupervised learning for data mining. So uncover some meaningful patterns in the data. So this is a brief recap. So in a nutshell, data mining is trying to transform data in something valuable. Okay. Not exactly a synonym, but a bunch of keywords that more or less describe the same activities that you do in data mining is called knowledge discovery in database. That is also the acronym of a well-known conference, international conference on the topics. Data mining and machine learning are not the same thing, obviously. Machine learning is more of a family of techniques, whereas data mining is more of a problem, okay? So machine learning has to do with learning a model to do something with the data, okay? Application, forecasting, prediction, maybe generating new data. In the case of reinforcement learning that we will most probably start today, also generate strategies for action, okay? Data mining instead is more of a, if you want, is more of a search task. Okay? You are looking for something. Of course, as I said, there are many areas of overlapping between the two fields. A classic example of data mining, and this will be the example that we will use for also to introduce association rule mining, is the so-called basket analysis. Okay, this may mean a lot of things. It could be marketing basket analysis. It could be something else. It has nothing to do, unfortunately, with the sport of basketball. Okay, and the most easy to grasp example is, and also one of the earliest application of machine learning, is the supermarket analysis. So suppose that we have a database of data that regards basically purchases at the supermarket by people. Okay. Obviously, the supermarket could be very interested in understanding whether there are some frequently occurring patterns in what people buy. Okay. Regularities, if you wish. Trends in the list of transactions that the clients of a supermarket perform. So, for instance, a classical example is, well, usually people who buy cereals and sugar also buy milk. That's trivial, I would say, okay? But there are many examples of this. And this is something, as I mentioned, as an anecdote, that is one of the first historical application of data mining techniques, statistical techniques in the industry. If you noticed, usually think that the items in supermarkets are not placed by chance or at random. Okay. Oftentimes, for instance, snacks like chips are besides beverages. Even if maybe one would expect chips to be, I don't know, besides something else, like food with salt or stuff like that. Okay. Obviously, they are together because it has been seen that people who buy some form of beverages usually buy chips, and the other way around. Okay. And there is a famous example of a supermarket chain in the US that moved beers near I don't know what. Moved beers, I remember. I will put this. Moved beers besides diapers for babies, for kids. Okay? Because when dads stay at home with kids, they need beer. Okay? So they moved beers next to diapers and increased the selling of both items. Okay? So this is a funny example. I guess you can imagine lots of these associations, okay, in your daily life, for instance. This is not very different from what? A platform, an e-commerce platform that I already mentioned during our lectures. Do you see some similarity with what one specific platform is doing? Don't be shy. Amazon, for instance, and what is the specific features that? Yeah, when you buy something, people who bought this also bought this. That's the same. Basically the same. Okay, that's basically the same. So, and you can imagine the same is done for I don't know phone plan software. Okay, you have this plan for your smartphone. People who had this plan also had purchased this one. So let's offer this plan. So this sort of analysis is pervasive in the industry, especially in retail. Okay. Again, this is not, basket analysis is not a synonym of data mining, okay? Data mining also includes other things. Basket analysis is one example of data mining activity. So let's try to better define the problem. We have a set of items, basically, okay, which can be purchased or not. And then we have a set of transactions that include these items. Each transaction you can model, this is one way of modeling the problem. Each transaction is a binary vector. So all of the elements, each element is binary, 0 or 1. And obviously, having one element at 1 means that the corresponding item, okay, in our item set I, was purchased in that transaction. You can imagine the transaction as your receipt when you exit the supermarket, for instance. Instead, that specific bit of the transaction is 0 if a given item has not been purchased. We say that a given transaction, TJ, satisfies X, where X is a subset of items, not all the items in the supermarket, but a subset of them, if for all the items in this subset, they appear in the transaction. So basically, a transaction satisfies a given subset of items if all of those items have been purchased in that transaction. Obviously, this is a, let's say, mathematical definition of the problem. So here we had a huge data set of all the items sold by the supermarket. Here we have a data set of a huge data set of all the transactions that occur in the supermarket, and ideally, conceptually, in every transaction, all of the items are contained, but some items have a zero, have not been purchased. Okay? Obviously, in practice, this is not necessary. We can only keep record of the purchased items. And now what do we mean with the term association rule, which is in the name of the family of techniques we are now introducing? So association rule mining. An association rule is an implication where an item set, okay, implies another in general. So X is some subset of the items in the supermarket, okay, and IK, so the implication is of the form X implies IK. IK instead is not in X. Obviously, an item in the supermarket, but not in the subset denoted by X. This is the simplest case. In general, we can have multiple items on the right side of this implication. We have multiple items and implying multiple items, but this is the simplest and also most used example. So basically, we could have something, an association rule could be an implication such as cereal, milk, sugar, for instance. Or the example was cereal, sugar, milk. Meaning that whatever transaction includes cereal and sugar is likely to also includes, not is likely, but also includes milk, for instance, okay? This is the definition of an association rule, an implication, a logical implication. Seeing this implies that. Now, this implication is not always so certain, okay, as we formally stated. So we define a few, let's say, numbers, a few properties that tell us something about each association rule we may want to discover. So for instance, we define with the term support, okay, of an item set, so a set of items, multiple items, as the fraction of transactions that contain that items. I have my whole database of transactions. How many of these transactions include my item set? How many on the total number of transactions? That's the support, okay, of my item set, not of the association rule, of my items. Okay, so if I am interested in the support of the item set cereal, milk, sugar, no association rule involved. I'm looking for these three items. I check all my transactions and I count how many of them include these three items out of the total of the transactions. That's the support. Based on the support, we can define when an item set is set to be frequent. Okay? A frequent item set is one that has a given minimum support. Okay? We establish a threshold, and we won't be able to, let's say, avoid this threshold. We set a threshold, and we find only those item set frequent enough. So I only want item set with a support of 90%. Okay, so I'm only caring about the item set that appears in 90% of my transactions. Okay? Obviously, a small corollary implication to this definition is that every subset of a frequent item set is itself frequent. If my item set is cereal milk, okay, obviously both cereal and milk taken in isolation will be frequent. Okay. Let's assume that cereal and milk has a support of 95%. For sure, both cereal individually and milk individually will be a support of at least what I said, 92%. It can be higher, it cannot be lower, obviously. It can be higher because each of those can also appear individually in my transaction. It can be higher, but it can't be lower. So basically, we defined what is the support of an item set and trivially how to define how a frequent item set is defined, simply chose a threshold. Now we can define the support of a rule, for instance. Support of a rule, so not of an item set, but a rule. So an antecedent, a left-hand side, an implication, and a consequent, a right-hand side. The support is, of course, the fraction of transactions that contain what? The union, okay, of the left-hand side and the right-hand side of the rule. So basically, it's nothing very different from the frequency and the support of an item set. Just forget about the implication, pick the union of the left-hand side and the right-hand side. That's the support. Okay, so if we have a rule, the support is defined of this rule is defined in the intuitive way with respect to the support of an item. Pick the union of everything you have on the left side, cereal, sugar. Everything you have on the right side, milk, that's the support. Count those transactions, okay? Transactions that include those items. What is the confidence instead? All these measures will be used by algorithm to find meaningful rules. The confidence of a rule is again a ratio, like the support, is the ratio between the support of the rule, and when I write in the slide the support of a rule, I mean the support of the antecedent of the rule union with the consequent of the rule, so the whole rule, divided by the support of only the left-hand side, the antecedent. That's the confidence, okay? So if I have the usual rule, cereal and sugar implies milk, I would have the support of the whole rule, cereal, so looking at transactions that include cereal, sugar, and milk, calculating their support, and then dividing this number by the support of only the antecedent. So the ratio of transactions that only contain cereal and sugar. That's the confidence. Okay, how confident am I in my rule? This ratio. Intuitively, the confidence measures exactly how much data supports your rule intuitively. Let's do a practical example. Everything should be quite easy. But anyway, let's have a look at a practical example. So here is our data sets of transactions. So basically the columns are the I database, so all the products in the supermarket. Maybe not all the product, but this is just a subset included in these transactions. And the rows are actually the transactions database. So for each transaction, which specific item has been is included in that transaction, so has been purchased in that receipt, let's say. Okay, so we have milk, cereal, biscuits, ham, tea. So let's assume that we want to find out whether milk and cereal and tea and ham are frequent items. To to answer this question, we must set a threshold, as we said. We must establish when, above which threshold, we consider an item set to be free. Let's fix it at 30%. This is arbitrary, okay? Obviously, we can already guess that the choice of this threshold influences, for instance, how many associative rules we can find. Okay? Setting a higher threshold, we find less rules because we want to be very certain of our rules. So, milk and cereal, there are no rules involved yet. We are only talking about item sets. Milk and cereal occur in 3 transactions together, okay, occur together in 3 transactions out of 5. Dad, tea, and ham occur together only in 1 transaction out of 5. So, according to our set threshold, milk and cereal is a frequent item set because the frequency is 60%, okay, the double of our threshold. Whereas here, tea and ham is not a frequent item below our threshold. Let's do the same for a more complex set. Milk, cereal, and also biscuits. Are they still a frequent item set? I would say yes, 2 out of 5, so 40%, still above 30. And obviously, if we complicate ham and tea, there is no chance that this is frequent. Remember what we said before, the implication works with subsets, not supersets. The previous item set tea and ham was not frequent. It is impossible that a superset is frequent. Instead, these items in isolation could be frequent. For instance, in the case of tea, that will be a frequent item. Okay, occurrence is. So remember the implication. MCB is a frequent item set. BHT is not a frequent item set. We are not surprised. T and H was not a frequent item set on its own. Now let's consider these association rules. Okay. The definition of whether these rules are frequent is the same, obviously. But we are not interested usually in frequent rules or the support of a rule. Usually we are directly interested in the confidence. So let's try to compute confidence and support for these rules. Milk and cereal implies biscuits. Cereal and biscuits imply milk. Intuitively, this is a toy example, so maybe it is not the case in this toy example, but intuitively, cereal and biscuits probably are more likely to imply milk than milk and cereal. Maybe I like cereal and I don't like biscuits. If I buy both cereal and biscuits, probably it's likely that I buy some form of milk. This is just based on my personal expertise. Okay, so maybe we will find out a different example here in this toy scenario. So let's try to work with milk and cereal implies biscuits. The support is 0.4. So we are looking for the support at all the transactions that includes both items. So milk and cereal, 1, 2, 3. Okay, milk and cereal, 3 out of 5. No, sorry, and biscuits too. So only 2. Milk, cereal, and biscuit, the union of the antecedent and the consequence. So only 2 out of 5. 40%. And then if we want to compute the confidence, If you remember, we have to divide the support of the whole rule by the support of only the antecedent, milk and cereal. Milk and cereal is the one I calculated before by mistake, so 1, 2, and 3. 3 out of 5, 60%. If we compute this ratio, the confidence of our association rule is 66%. What does it mean? In a sense, as we anticipated, our interpretation is that let's say a considerable portion of our database of transactions supports, okay, our association rule. Gives evidence that this association rule holds. We will now also introduce other measures, and the reason is that if you think about it, the confidence doesn't tell us anything about what if, doesn't tell us anything about how, in what ways seeing one of these items increases the probability of seeing this other item. Okay, it is very similar to the raw notion of support. Now we will introduce some other measures. The other example was cereal and biscuit that imply the purchase of milk. So again, let's compute the support, so the union of left and right hand sides. Cereal, biscuit, milk, they are the same. You notice only the order changed, so the support must be the same. Okay? If you have different supports for a rule that includes the exact same items, obviously you are wrong. Okay, so the support is the same. We are looking for the same 3 items. We only changed the order. So M, C, B, M, it's the same. 1 transaction and 2 transactions, 40% of support. What may change instead, obviously, is the confidence. Because now we have to divide this support of the whole rule by the support of only the antecedent that changed. The antecedent now is no longer milk and cereal, but it is cereal and biscuits. For cereal and biscuits, we have 1 and 2 entries out of 5. Again, 40%. The confidence of this rule is 100%. So this toy scenario confirmed our intuition that if you buy cereal and milk, it is, we would have said almost certain. According to our evidence, it is certain, absolutely certain, that you will buy also milk. Speaking of measures, so trying to understand what my rule is telling me and how much, basically, all of the measures are the same measures that we have seen for supervised learning. Basically, they tell me how much can I trust my discoveries. The lift of a rule is defined this way. Basically. So the ratio between what? The support of a rule, so our usual friend, the support of a rule, okay, and the product of the 2 supports, the antecedent and the consequent. So if you want to remember the formula, basically you have 2 ways, because either you remember this formula or you notice that actually embedded in the lift there is the confidence. Support A and B divided by support A, so the antecedent, is exactly the definition of confidence. So the lift basically is the confidence of the rule divided by the support of the consequent. Why this measure? Why to introduce this measure? This measure tells us a little bit more than the confidence in a rule alone. The confidence is always, let's say, a relative term, okay? So it's a percentage, basically. you can see the confidence as bounded between 0 and 1 or 0 and 100%. The lift instead can be 1, -1, more of 1, with no bounds. Having a positive lift greater than 1 implies that the two item sets, the one in the antecedent and the one in the consequent, has a positive correlation, basically. It means that, how can I say? When the antecedent is present, the consequent is present in the transaction in your dataset, the consequent is more likely to appear than if the antecedent wasn't present. That's why it's called lift. Seeing these items, the antecedent, increases my likelihood of seeing the consequent. Okay? Obviously, lift lower than 1 is the opposite. So these items appear together less than I would expect. And lift equals 1 basically means that you have no evidence to draw whatsoever conclusion, okay, about seeing the antecedent on the likelihood of seeing the consequent. There is one, caveat is the correct word. One, if you want, limitation of the lift. Since in the lift, basically, we are only checking the support, okay? So we are only reasoning in terms of item sets. Basically, the lift is a symmetrical measure. The lift of a rule with antecedent A and consequent B is the same as the lift for antecedent B and consequent A. This may be not actually the ideal situation, okay? As we have seen, changing the order of the items in an association rule an impact, okay? This rule is much more likely than this. So having this sort of symmetry in the lift is not really an ideal situation. Nevertheless, the lift is a very useful measure, basically to understand whether seeing items together is more likely than seeing items separate. Usual example, I will guess the same exact dataset. So we have the same exact, if my memory is right, rules, but we compute the lifts this time. Okay, so again, in any way you can see, you want to see it, it's the support of the whole rule divided by the product of the two supports. So let's start with milk and cereal implies biscuit. Again, the support of the rule is the same, 0.4. We already computed the confidence, that was 66%. We can compute the support of the antecedent. We already have that for the confidence. So all of this data, we already added. Okay, that's known data. The new thing we need to calculate that we didn't need before is the support of the consequent. So biscuits appear in 1, 2, 3, 4 transactions out of 5. So 80%. Now let's apply the formula, whatever if you're using the confidence or if you're using the raw numbers. In this case, we are using the known numbers. So support of the whole rule divided by the support of the antecedent product times the support of the consequent. This is our lift. Okay, so actually, all these items together are basically less likely to appear than taken in isolation. If you take them together or in isolation, it is less likely to see them together. I would say that this is according to our intuition. If I buy milk and cereal, maybe I'm only interested in milk and cereal, not in biscuits. So, again, according to our intuition, the other lift should be instead more than one, according to our intuition. Let's check. So, only the order of the items changed. Okay, so the support of the whole rule is the same. The support of the antecedent different from the previous, but is the one we already computed here. And if we now apply the same calculation to the lift, we find that the lift is above 1. And that's, again, according to our intuition. Seeing all these items together is more likely than seeing those items in isolation, separate. Okay? Basically, that's what the lift is saying to us. Keep in mind, probably you don't remember that we already mentioned the Bonferroni principle, but which is not a mathematical theorem or something, okay? It's just, let's say, a word of caution. Association rule mining is particularly dangerous, okay? Likewise, some supervised machine learning technique that we've seen, we mentioned that this technique is prone to overfitting or what? Well, association rule mining is dangerous in the sense that depending on how do you set the threshold for considering frequent items, depending on the threshold you consider to, for instance, the confidence. So I don't want rules with low confidence, whatever. You are obviously more or less likely to discover patterns that are not really meaningful, okay? What does it mean to have a non-meaningful pattern? Well, two big categories. One is the one in the slide, spurious pattern. It is just by chance that you find that correlation in your data, okay? That could be pure chance. You have limited data, you set maybe the threshold too low, and by pure chance you find out that, I don't know, people who buy pasta also buy ketchup, but we are in Italy and we don't put ketchup on pasta. Okay. So the other meaningless pattern is could be a trivial pattern. Okay, maybe milk and cereal can be considered a trivial pattern. Okay. That is something that I could have inferred without the help of association rule mining. So every time, this is not new, okay? Every time you apply association rule mining, exactly as every time we apply any kind of model and we get back a accuracy measure, don't take just the raw number, but reason about whether what you are finding out makes sense. So association rules are particularly prone to basically confirm your existing bias. I'm looking for a rule, for an implication, and the dataset confirms my prior bias. Okay, try also to falsify. Are there other rules different from this one? What if I change the order of the item sets and stuff like that? There are other measures that are involved in association rule mining. One in the interest, although the interest is somewhat similar, very, very similar to the lift in the sense that basically gives you the same information. This time we have a difference, not a ratio. And the interest of a rule is the confidence of the rule, again, our usual measure. This time we do not divide by the support of the consequent, but we remove the support of the consequent. Okay, so we perform a difference. You remember in the lift, we had the confidence divided by the support of the consequent. Now we are not dividing, we are doing a difference. Okay? If A, so the antecedent has no influence on the consequent, okay, antecedent and consequent, the number of transactions contained in both A and B should be exactly equal to the number of transactions that contain only B. So the number is 0, and this rule, it is said to have no interest. Okay? Basically, it means that B only appears when also A appears. That could be, for instance, a trivial rule. I would to make an example, but well, the milk could be an example. No, I would say, because the milk can be bought independently of cereal. Trying to do an example, but I really haven't one. Yeah, but basically this interest is exactly 0 only for those items that actually make sense to purchase only together. Instead, if a rule has a large positive interest, this again is a measure that is unbounded. So you don't have any reasonable range. If a rule has a large positive interest, it means that the fractions of people that buy A, the antecedent, and that also buy B, is much larger than the fraction of people that only buy B. This is meaningful. Okay? It means that buying A increases the chances of buying B. What do I mean by meaningful? If you're working in a supermarket, move the items A closer to the items B. If they buy A, they are more likely to buy B. Okay? That's an indication. Instead, the opposite holds for large negative interest. The people who buy B are unlikely to also buy A. So who buy the consequent is less likely to also buy the antecedent. So they are, say, opposite correlated. Usual example to compute the interest. The first two measures are already known, confidence and support. This time we take them as percentages, but we could also take the numbers. It doesn't really make a difference. The interest is negative, which means people who buy the consequent, okay, this is not large, but it is nevertheless a negative interest. People who buy the consequent, biscuits, are not likely to buy more milk and cereal. The opposite is true instead. For people who buy cereal and biscuit, they need milk, and in fact, buying milk increases also this chance. Okay. Last, if I remember well, the last measure that is interesting also because it has, if I remember well, correctly, as given bounds, is so-called the conviction of a rule. And basically, it's the rate of the expected frequency, okay, that a given item occurs without another given item, okay? So, when you see in the formula y hat, this means this is the support of not having that item in your items. Okay? So we are looking for zeros this time in our table, not for ones. Okay, so we are looking at the rows where this given item appears with a 0. Okay, that's the hat, a negation basically. So if we have a rule, I don't know why I changed the letters. If I remember, I will fix the slide because it makes no sense. So if we have the usual rule AB, okay, we compute the support of the antecedent, we multiply by the support of not seeing the consequence. So we are not looking for rows in our dataset in which B appears with a 1, but in which B appears with a 0. And then we divide by this intersection. This is an intersection, not a union. So the support of seeing together the antecedent and not the consequent. If you wish, equivalently, you can see the conviction as 1 minus the support of the consequent, 1 minus the confidence. In this case, this, at least for me, is easier. Okay? But basically, the derivation is obvious. Usually, we work with unions, not with intersections. So we have 1 minus the confidence, because the confidence of the rule is the union. And here, obviously, we want 1 minus the support of 1. Because we are taking the zeros and not the ones. So again, let's try to do the computation for milk and cereal implying biscuits. We compute the confidence. We compute the support. We chose this rule simply because we already have added this measure, so it's easier. And we compute the conviction, 0.6. What does it mean? Let's do the opposite. So milk and cereal implied biscuit has a conviction of 0.6. Let's try the opposite. That intuitively we said is the most reasonable rule. So cereal and biscuit imply milk. If you do this computation, now we have a special case, and the case that, for instance, in implementation must be handled with care, okay? Because computers don't like divisions by 0 usually. If you have a division by 0, okay, usually the computer crashes. The whole computer, your calculation crashes, gives you an error. But instead, that's a good news for us. That's maximal conviction. The consequent, the milk, is highly likely to depend on this specific antecedent. So having higher conviction is, for us, good news, as we would expect. For the conviction, we don't have this sort of specific boundaries that we had for lift. Okay? So it is a bit more difficult to reason about conviction. It is not so common to have plus infinite conviction, so it may be not so easy to reason about, okay, what about having conviction 0.6 or having conviction 10? Intuitively, 10 is 1 order of magnitude more than 0.6, okay, but you have no specific bound. So what we did up to now is only defining what an association rule is, right? And how to compute some metrics to assess whether the rule is useful, meaningful, or not. We didn't say anything about how to find these rules. Okay. After the pause, we will introduce the, let's say, basic algorithm that is not the most up-to-date regarding the state of art, but I would say that most of algorithms are still based on this very simple idea called a priori algorithm. It is there for 30 years.